For the next big chunk of the course, for the next few weeks, we'll be talking about proofs. And the book has many chapters on proofs. We'll be going through almost all of them. Not entirely, but in parts. So, proofs is a very important part of mathematics. We couldn't do mathematics without proofs. So we're going to start simple, but build up to a more sophisticated ones. Now, before we can do proof, first, let's just explain what a proof is. Well, a proof is just something that shows a statement to be true. So remember, a statement is a claim that is either true or false. In math, we often want to prove that something is true, so we can use a proof for that. We can prove that a statement is true. In other words, give some evidence or reasoning to show that give reasoning to show that the statement is true. Now, before talking about proofs, we want to have some definitions because proofs rely on usually proofs rely on definitions. Like you're trying to prove that something fits some definition. So we need to start with some definitions. So we're going to start with defining a really, really simple thing, something that's intuitive to everyone: even. The idea of an even integer. So the definition is as follows: an integer n is even if n is equal to 2 times a for some integer a. Okay, now this word sum does not necessarily mean more than one, does not necessarily mean multiple integers a. The idea is at least one. One is enough. Some integer a. I could have said for an integer a. Okay, here's another way of putting this. An integer n is even if there exists an n in the set of integers such that n is equal to 2 times a. Let's look at an example. So we know that 10 is even. Why is that according to this definition? Well, we have to find, so 10 is our n. We have to find this 2 times a. We have to find this integer a such that when I do 2 times a, I get 10. Well, here it is. 10 is equal to 2 times 5, and 5 is an integer. 5 is an element of z. So we satisfy the definition of even number. 10 satisfies that definition, so therefore 10 is even. How about 11? 11 is not even, but why is that based on this definition? Well, the reason is there is no integer a such that 11 should be equal to 2 times a. If you solve for a, you'll get a fraction, right? Not an integer. You will not get an integer for a. So the point is there is no integer a that would make this thing be true, that would make it so that 11 is equal to 2 times a. So therefore 11 is not even. Now there's an important convention to keep in mind, and whether this is a good convention or not is not for me to say. I happen to think it's a bad convention, but this is the convention that mathematicians generally use, and that is that definitions are usually phrased in the conditional form, even though they are understood as biconditional statements. Right? So this definition was expressed as follows, right? An integer n is even if something, right? So it's in the form of something if something, right? So if p, then q, right? Or q if p, but it's phrased in the conditional form. But we understand definitions generally as biconditional statements, that if p, then q, and also conversely, if q, then p. So let me show you. So for example, for this definition that we have above, based on the above definition, we know two things. First of all, we know that if n is equal to 2a for some integer a, then n has to be even, right? So we see if n is equal to 2a for some integer a, then the integer n is even. But we also know the converse, right? We also, even though it doesn't explicitly say if and only if, but it's implied, the converse is implied, which is that if n is even, then n is equal to 2 times a for some integer a. So again, this is showing that this above definition is understood as a biconditional statement, even though it's technically written in the conditional form, but that's just a convention. But we mean that it is a biconditional statement, that an integer n is even if n is equal to 2a, and also conversely, if n is equal to 2a, then if sorry, if n is equal to 2a, then an integer n is even. And then conversely, if n is even, then we know that n is equal to 2a. Now we have the definition of an odd number. An integer n is odd if n is equal to 2a plus 1 for some integer a. So for example, 13 is odd. So 13 is our n. We have to find an a such that n would be equal to 2a plus 1. So we need to find something that 13 would be equal to 2 times a plus 1. Well, here it is. 13 is equal to 2 times 6 plus 1. And we know that 6 is an integer. So 13 satisfies the definition of an odd number. So therefore, 13 is odd. Now we have some really, really basic axioms like, building blocks without which we couldn't create proofs. Now we're not going to prove these axioms, but I suspect that no one will doubt them, and they could be proven using more sophisticated math that we aren't going to get into in this course. But these are things that, well, not sure which course would be. Anyways, so here are the axioms. They're really basic. So suppose we have two integers, a and b. So again, suppose a and b are elements of z, right? So we have one element of z, a, another element of z we call b. So we have two integers. Then a plus b, so the sum, I take a and b and I add them together, that result is also going to be an integer. Also, a minus b will be an integer. Also, a times b will be an integer. Okay, so again, if I take any two integers and I either add them together or I subtract one from the other, or I multiply the integers together, the result of that operation will be a new integer, or will be an integer, maybe the same integer, but will be an integer. Okay, now we're not proving these axioms, but we're going to be using them heavily in our proofs. So we're taking them as granted. We're not proving them, but I believe they could be proven. I'm not certain about that. I think they can be. Okay. For example, let's say we know that a, b, and c are integers. And then let's say we have a squared times b minus ca plus b. Okay, this thing here, whatever it is, this result that we get from this expression has to be an integer. Why? Well, a squared is a times a, so that's multiplying one integer by an integer. An integer times an integer is an integer, so this is an integer. Then we take that and multiply it by b. We know b is an integer, and we're multiplying one integer by another integer, so we get a new integer as a result. Now we do c times a, that's again multiplying two integers, so we get an integer as a result. Then we do subtraction of one integer from another integer, so that's going to give us an integer. And then we add an integer. So we take an integer and we add an integer, we get an integer as a result. The point is, since we're dealing with integers here and we're just doing addition, subtraction, multiplication, with also including exponentiation, because that's just it's just a shorthand for multiplication, right? A squared is just shorthand for a times a, so that's also counted as it's also considered multiplication. So we know that this result is going to be an integer. Okay. All right, now we're going to start with the first type of proof that we will learn about in this course, and that is direct proof. And so here's going to be an outline just showing the general form of a direct proof. We're going to see that different kinds of proofs have different general outlines. So direct proof, here's the outline. We start with a proposition. Proposition means the thing that we want to prove. It's like a statement. Basically, it's a statement. Here's the thing that I want to prove. And it will usually have the form, it will actually, for a direct proof, it has to have the form if P, then Q. If P, then Q. So if something, then something. That has to be the form. Now, this could be a little more complicated, right? It could be like if something and something, then something else, right? That's also okay. But the point is it has to be an if-then kind of statement. That's our proposition. Now we want to prove it. The proof is going to look something like this. We're going to start by saying, suppose P is true. We're going to do a bunch of steps in the middle. And this is where the hard part is. And that's where the creativity comes in, right? You have to sometimes be creative in coming up with those middle steps. where the dot, dot, dot is over here. And then our bottom line is, the bottom line of the proof should be something, therefore Q. Whatever this Q is, therefore that. The idea is we have to show that by supposing P to be true, that leads directly, step by step, it leads directly to Q being true. By doing this, we have thereby proved that if P then Q. Because what does if P then Q mean? It means that whenever P is true, that forces Q to be true, meaning P leads to Q, right? P leads to Q. So how do we prove that? Well, we say, let's say I know that P is true. I will show that that leads to Q being true. Okay, so that's what we're going to do in a direct proof. Here's our first example of a direct proof. So first, here's the proposition that we want to prove. The proposition is fairly simple. It says, if x is odd, then x squared is odd. Okay, so before we go further, before we go to the actual proof, let's do some examples. So let's say n is equal to 3. Right? X is odd. I'm sorry, I should have used x here instead of n. Okay, but whatever. If x is 3, then x squared is 3 squared, which is 9, which is odd. So the proposition is true for x equals 3. Okay, but that's not enough, because the proposition is a sentence of the form if P then Q. And if you remember from the videos on logic, when we have something of a sentence of the form if P then Q, we generally assume that it's universally quantified, meaning that the claim of this sentence is that it applies to all values of x, meaning in this case, all integers, because if we're talking about odd, then that only applies to integers. But the idea is that this proposition, even though it never explicitly says that this applies to all integers, but it's implied in the proposition that it applies to all integers. So here we have one example where n is equal to 3, but that doesn't prove the proposition. That just shows that it's true in one particular case. Let's try another example. So let's say we have x equals 5. Well, then x squared is going to be 5 squared, which is 25, which is an odd number. So that also fits with the proposition. So that's a good sign. Let's say we tried a negative number. Right? We were only doing positive numbers until now, but the proposition never says anything about positive or negative. So let's try a negative number. So let's say x is negative 3. Okay, then x squared would be negative 3 squared, which is 9, which is again odd. So that seems to work. So some of you might say, well, maybe all of you might say, well, this seems to be a pretty solid proposition. We tried it out a few different cases. We tried positive, we tried negative. It seems to be proven, right? What more do we need to do? Well, please don't do that on the test, because you won't get credit for that question then. But I'm going to show you a little soon why we don't do this kind of thing. But the idea is that, you know, we just showed that it works in a few examples, but how do we know it works in every single possible case of an odd number, right? How do we know it works for 1,000,001, which is an odd number? How do we know, right? How do we know that 1,000,001 times 1,000,001, right? 1,000,001 squared, how do we know that is odd? Right, of course, we can check that manually, but then what about the next odd number and the next odd number? So we're dealing with an infinite number of possible odd numbers, right? An infinite number of odd numbers. So we can't just check all of them. So so we need a better way of doing this. So, you know, this is a way that math is different from all other fields, really, all other fields in every other field, even in the sciences. You know, so if you're a physicist and you run an experiment, you know, 1 billion times, and you get the same, you know, the same result every time, or, you know, your result aligns with your theorem, the result of the experiment aligns with your theorem every single time out of those 1 billion times, you would probably consider your theorem to be very strongly proven. But in math, that wouldn't be worth anything, really. I mean, it would maybe lead us to want to believe that the theorem is true, but it wouldn't prove it at all. We would still need to come up with a proof that works, that's a general proof, that doesn't just give me examples. So examples aren't, the bottom line is examples are not a proof. We will see in a very small situation, in a very unique case, an example can be a proof. But for the most part, examples are not proofs. So as many examples as you give, it's not going to be a proof. So don't do that on the test, please. So let's see how we actually prove this proposition. So again, we're trying to prove that this is the case, that this will be the case, that this proposition will apply for all odd numbers. So so again, remember the form of a direct proof is we suppose that this is true. So we suppose that this is true, and our goal is to show that this is true. Right? So the bottom line of the proof is going to be, therefore x squared is odd. So that's what we're working toward. We suppose x is odd, and the bottom line that we're working toward is that x squared is odd. Okay, so now what do we know if x is odd? So the idea is when making a proof, at each step you have to think about, what do I know? What do I know? What can I determine based on what I have so far? So if I know x is odd, so then following the definition of an odd number, then, hold on, this is a mistake, x equals 2a plus 1. So I have to fix that. So since x is odd, we know that x has to be equal to 2a plus 1 for some a and z. So there is some integer a that makes this thing be true. Okay, so now let's try to figure out what is x squared going to be based on the fact that we know that x squared can be expressed as 2a plus 1. So thus, x squared is going to be equal to 2a plus 1 squared, which is equal to 2a plus 1 times 2a plus 1, which is equal to this, right? So we do 2a times 2a, we get 4a squared. Then we do 2a times 1, that's 2a, plus 1 times 2a, that's another 2a. Together we get 4a. And then we do 1 times 1, which is 1. All right, now we're trying to show that x squared, that this thing here, x squared, we're trying to show that it is odd. So can we show that this thing here is odd? In other words, we have to put it in the form of an odd number. We have to show that it is equal to 2 times an integer plus 1. Well, here's how we can do it. We can factor out a 2 from these two terms, which leaves us with 2 times, and then in parentheses, 2a squared plus 2a. And then we have the plus 1 at the end. Now, what we have is x squared in the form of an odd number. Why? Because we have x squared is equal to 2 times this plus 1. Now this, in parentheses, is an odd number. How do we know it's an odd number? How do we know that 2a squared plus 2a is an integer? I'm sorry, we don't know it's an odd number. I'm sorry. We don't know it's an odd number. My bad. We know it's an integer, right? We know this thing in parentheses is an integer. How do we know it's an integer? Well, we started out that a is an integer. We know a is an integer because we said that's what x is equal to 2a plus 1, right? X is equal to 2a plus 1, so that a has, and we said for some integer a. So we're defining a to be an integer from the beginning. So now when we have 2a squared plus 2a, that's just doing addition and multiplication with integers. So the result is going to be an integer. So we know that 2a squared plus 2a is an integer. So now we have the form of an odd number. Thus, x squared is equal to 2 times b for some integer b. Right? Again, we have the form x, x squared in the form of an odd number. Therefore, x squared is odd. And that's the end of the proof. So how did that go? We said suppose x is odd, and we concluded that if we suppose x is odd, we are forced to conclude that x squared is odd. So that proves that this proposition is correct, because that's exactly what this proposition says. It says that whenever x is odd, that forces x squared to be odd. If x is odd, then x squared is odd. And we showed that just by supposing x is odd, x can be any number as long as it is odd. If x is odd, x squared must be odd. Again, this reasoning applies to every odd number. This is not examples. This is not giving an example. This is giving reasoning that applies to every odd number. All the details here in this proof work the same for all odd numbers. So any odd number x. So so that's why it's a conclusive proof. Okay, great. Now let's talk about why don't examples suffice, right? For the previous, proposition, why couldn't we just give a few examples, maybe 5 examples? Why wouldn't that be enough? Right? After all, when you test a program, how do you test it? Right? You test it with a bunch of examples, and then you consider it. If the program passes all the tests, and it's you have to put some thought into making those tests. You can't just pick any random tests, but you give some thought and you make good tests, and you package up the program, and then it's good, right? You're all done. You can send it out to your clients. Whatever, it's ready to run. It's ready to run, right? It's ready to it's ready to go once it passes the test. So what you're doing there is just giving some examples and showing that the program works for those examples. So as programmers, we're used to that idea, but in math that is not enough. Math examples do not suffice. So here I'm going to give you 2 sort of examples. Okay, I know it's a little ironic. I'm going to give you 2 examples that show you why mathematicians, give you an idea of why mathematicians don't like to just give examples. The real reason is because examples don't prove anything. I mean, they don't. I mean, they give you maybe a high degree of probability that something is true. So those tests that you do on the program, give you a high degree of probability that the program works in all cases, but you can't prove it. In fact, it's impossible really to prove, except in very small cases that a program is going to that a program is going to do exactly what you think it's going to do in all cases. Anyways, here are 2 interesting examples. So here's a proposition: if n is a non-negative integer, okay, any non-negative integer, then n squared plus n plus 41 is prime. Okay, this is a proposition. We know what a prime number is, right? It's a number that has exactly 2 divisors, namely 1 and the number itself. So like 5 is a prime number, 2 is a prime number, 17 is a prime number. Okay. So this proposition says if n is a non-negative integer and I do n squared plus n plus 41, that result is going to be a prime number. Well, let's try some examples. So here are some examples. So we're going to have value for n, and then n squared plus n plus 41, and we're going to see whether it's prime or not. So if n is 1, then the result of that expression is 43, and that is a prime number. So that seems to be good. How about 2? That also works. How about 3? That also works. And so on. We can keep going with examples. And we can, for example, 39. For that, we get a result of 1,601, and that is a prime number. So, we can try so many examples here, and they all work, including all these numbers in between. Everything between 3 and 39, it also works. All these numbers here that I didn't list out are also prime. So question, is this proposition true? Well, it's actually not true. And here is a disproof of the proposition. So a disproof is basically a proof that the proposition is false. It's a proof that the proposition is false. So it disproves the proposition. So here it is. When n is equal to 40, so it's a non-negative integer, n is equal to 40, we have that n squared plus n plus 41 is equal to 1,681, which is equal to 41 times 41, which therefore isn't prime because it has more than 40 has more than 2 divisors. One of the divisors is 41. So the idea is, that this is just a nice example showing that giving examples isn't enough. All right, here's another a more famous example. So this is something called Euler's conjecture. A conjecture is something that a mathematician or mathematicians think is true. They suspect is true. They want to think is true, but they don't actually have a really good proof for it. Right? They may have reason to believe it's true, but they don't have convincing proof yet for it. So Euler is, by the way, yes, it's pronounced Euler, Euler, not Euler, Euler. He was one of the greatest mathematicians of history, probably, maybe second or third greatest mathematician, maybe some would consider the greatest mathematician in history, whatever, one of the greatest mathematicians in history. He had this following conjecture, meaning he believed the following was true. And that is the following: the equation a to the power of 4 plus b to the power of 4 plus c to the power of 4 equals d to the power of 4. So that's it. That's an equation. His conjecture was that this has no integer solution, meaning there's no way to assign integers to a, b, c, and d to make this equation be true. Again, the question is, can we assign integers, an integer to a, an integer to b, an integer to c, and an integer to d, to make this equation true? That's what we want to know. So Euler said, no, this has no integer solution. Now, for over 200 years, after Euler made this conjecture, people tried many different examples for a, b, c, and d, but none provided a solution to the equation. Question: so was the conjecture considered proven? After all, they tried many, many examples. I don't know how many, but they tried many different examples for a, b, c, and d. None of them work. So it seems like there is no integer solution. So was the conjecture considered disproven? Answer is no. Okay, and that's just going along with what we're saying, that examples don't prove anything. And in fact, eventually someone found the solution to the equation. When you have these four numbers, a, b, c, and d, that provides a solution to the equation. In other words, we have the following disproof, right? This thing here shows that Euler's conjecture is false, because this is in fact a solution to the equation. By the way, the person who found this solution was a 22-year-old graduate student. Okay, but he's a very accomplished 22-year-old. Okay, you could, I think I forgot his name. This was in the 1980s. You could look on Wikipedia for Euler's conjecture. Okay, so now let's do another direct proof. Here's a new proposition. It says if x is an even integer, then x squared minus 6x plus 5 is odd. Okay, so that's, we can try a bunch of numbers, we can try a bunch of examples, and if all those examples will work, but that won't be considered a proof. So we need to give a general proof to show why this is true for all even integers. That if x is any even integer in the world, then x squared minus 6x plus 5 is going to have to be odd. So let's start. So as usual, it's a direct proof. So we say, suppose x is an even integer. Our goal is to show that x squared minus 6 plus 5 has to be odd. That if we make this assumption that x is even, then this has to be odd. So suppose x is an even integer. Well, what do we know? Well, we know that x has to be equal to 2a for some integer a. This is just based on the definition of even numbers. If x is an even number, then x has to be equal to 2 times a for some integer a. So now let's try to plug that into x squared minus 6x plus 5. So x squared minus 6x plus 5 is going to be 2a squared minus 6 times 2a plus 5. So the 2a raised to the power of 2, notice this is the 2 outside the parentheses. So that becomes, it's like 2 squared times a squared. In other words, 4a squared. Okay, 4a squared. Then minus 12a plus 5. Now we want to get this in the form of an odd number. Okay, so here's how we do it. 2 times 2a squared, so that's 4a squared. And then minus 6a, so that's 2 times 6a would be 12a. And then 2 times 2 would be 4, so that's in parentheses. So 2 times that parentheses, and then plus 1. So again, we have 2 times 2, that's 4, plus 1, so that's a 5. All right, now this is in the form of an odd number. So in other words, thus x squared minus 6x plus 5 is equal to 2 times b plus 1, where b which is equal to 2a squared minus 6a plus 2, is an integer, right? B is equal to this thing in parentheses. And it's an integer. How do we know it's an integer? Because we're just adding, subtracting, multiplying integers inside it. So the result is going to be an integer. Therefore, x squared minus 6x plus 5 is odd, because again, we showed that it has the form of an odd number. That's the end of direct proof. We'll actually see a variation. No, that's wrong. We'll have more examples of direct proof coming up.